In this video, section 2.6, we're going to look at skewness and the mean median mode, the relationship of skewness to the measures of central tendency or the measures of the center that we already looked at. But before we really get into the concept of skewness, we're going to look at its opposite, which is symmetry. You're probably a little bit familiar with symmetry from the geometric symmetry. My hands are symmetric to each other. They're not the same, right and left, but they're mirror images of each other. Rectangle, symmetric this way and symmetric this way. In our case, symmetric data, or symmetric data is going to look like this. Here's the example I had to start with. My data is, let me just start a new line for it. 4, 5, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 9, and 10. So I'm going to separate them with commas. I mean, they're all one-digit numbers except for that one. So it's not too unreadable, except that there's a lot of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that would be, I would say n equals 16 because the total number of data values is 16. It ranges from 4 up to 10. You can see there's a lot of 7s. But here's a more subtle kind of symmetry. We're going to actually see a picture of this too. There's a bunch of 7s in the middle. You can probably tell that 7 is the mode. There are more 7s than anything else. But 8, one number up from 7, there are 3 of them. And also 6, one number down from 7, there are 3 of them. That's the kind of symmetry that we're looking at in data sets. Also, the next number 9 and the next number this way, 5, are one more step down, and then finally one up to the 10 and one down to the 4. So in a way, this is, you can see the symmetry already. I'm going to make a histogram. And this is really how we're going to examine symmetry for data. My number line needs to go down to 4, 5, 6, 7, 8, 9, 10. That'll be enough for this data set. And then for my vertical axis, the largest number of any individual data is, there are 6 7s. That's how high I'm going to need to go with my frequency axis. Actually, let me write frequency for this axis. This is the actual data value, or what we're going to call x. For the frequency, though, I need to go up to 6. So 1, 2, 3, 4, 5, 6 is enough. For 4, there's only one 4. So my block at 4, my rectangle only goes up 1. There's also only one 5, so that should only have 1 also. 6 has, there's 3 6s, so that's going to need to go up to the 3. This is 1, 2, 3, 4, 5, 6 on the frequency axis. The 7, as I said earlier, 7 goes all the way up to a frequency of 6. A little bit easier to do on paper, but this is turning out okay. There are 3 8s, 1 9, and 1 10. And it's a little bit lopsided. I think my numbers aren't evenly spaced here, but you can see the symmetry, the geometric symmetry along the line where 7 is. It's like from the 7s, we've got a step down and then another step down. And from on the other direction, it's a step down and another step down. So this is a better picture would be more geometrically symmetric. The one in my notes at the top there is not very readable, but it's a little bit better. This is the type of symmetry that you can actually see that comes from a data set making the histogram. What I want to say about that is a symmetrical, or symmetric is another word for it, but symmetrical distribution of data. And that's what we're looking at here. This data, it doesn't have anything to do with the numbers. It's how many of them there are, how many of each one. And that's what they're not symmetric numbers, they're symmetrically distributed. And it's a symmetric distribution. I want to mention for this example that the mean is equal to well, maybe it's not really clear what the mean's equal to from this, but if you add these numbers up and divide by 16, you get 7. And also the median, if I look at the middle numbers, the two middle numbers, there's an even number of numbers, 16. So the two in the middle, both 7s, the average of 7 and 7 is 7. And one more. I'm going to mention this also just to be a little complete about it. The mode is 7. I mentioned that earlier. There's more 7s than any other number, so it's the most frequent data value. And you can see it on the graph too. For the 7 block, it goes higher than any of the other ones. Now, what I want to emphasize about symmetrical distributions is that this is not a coincidence. For a symmetrical distribution, the mean, mu, is equal to the median, m. And that is kind of the defining characteristic of a symmetric distribution, that the mean and the median are equal. I want to say a little thing about modes. We're not going to work with mode very much, but there is something about modes that we can see in these graphs. In this case, they are going to be symmetric. So I want to make kind of a conceptual picture of the distribution. Now, we've been doing it with histograms, that's rectangles. This is a curve, but you can kind of see that higher frequency in the middle, lower frequency out at the edges sort of behavior. That's where this is the, well, I'm just going to call it the mode, because that's what we're looking at here. So there's the mode. It's the one that's the highest in the histogram. Now, some distributions, just for completeness, some distributions have two places that both have the same high value. It's not the same data value, but the same frequency for both of these data values. This is, well, that's the mode, and this is the other mode. They're both modes. This is called bimodal. And that's the word I wanted to introduce. If there's more than one mode, it's called bimodal. It's not a big deal as far as symmetry goes. You can see if there's, this one looks symmetric even though there's two different modes. This one looks symmetric with one mode. There's actually a word for that. Unimodal. Unimodal means that it has one mode. And this is by far the most common. This does happen occasionally. Here's an example. So I'm going to make a data set that's just 2, 3, 3, 4, 5, 5, and 6. And I don't want to make a histogram for this. You can see that it's symmetric just because it goes from the middle here. It goes down one for 2, and then down another one. And going to the right, it goes up 1 for 2, and then up another one. What I want to point out about this is modes are 3 and 5. This is a bimodal data set. There are 2 modes. There are 2 3s and there are 2 5s. They're both the most frequent data value. Now, if there's only one of each data value, they all have the same frequency. Are they all the mode? They are not. But if there's 2, that's enough to make it the mode in this data set. There are 2 of them, 2 modes. All right, let's get back to skewness. And the skewness that we're looking at is, in a sense, skewness is asymmetry. And we're going to see what that means for the data set. Asymmetric data sets are actually probably more common than symmetric. But for this one, let's start with an example where the data is, I've got a little bit smaller data set to work with for these examples, but 4, 5, 6, another 6, another 6, 7, 7, 7, a 7 and an 8. Actually, this looks a lot like that previous data set with the top 4 numbers cut off, the other 2 8s and the 9 and the 10. Oh, and a couple 7s missing too. Anyway, for this one, n equals 10. There's 10 data values. And I'm going to build a histogram so I can look at the data. So again, my number line comes first with, I need 4, 5, 6, 7, and 8. So 4, 5, 6, 7, and 8. And then for the frequency axis, the highest frequency is 4. So I really only need to go up 1, 2, 3, 4. So again, this is the frequency. These are the actual data values or X values that I'm given. All right, so let's build this. There's 1, 4, so I'm going to make the 4 block go up to 1. There's 1, 5, that's going to be the same height. There are 3 6s, so they'll need to go up to about there. 1, 2, 3, yeah. There are 4 7s, so that's going to be even taller. I don't really recommend these little hash marks as part of your drawing. It's easier to read it without those, but they help a little sometimes to construct and keep the y'all probably have lined paper. You'll be fine. And then there's a single 8 for the last block. Now this one looks like it's leaning to the right. Like maybe it started out as a symmetric thing and that got pushed to the right or something, or a pile of blocks that's pushed to the right. That's not what it's called though. This is called skewed left. So I said it looks like the blocks were pushed to the right. A better way to think of this is that from a pile of blocks, we stretch it out to the left. It's skewed left. I'm going to say the mean is pulled to the left. Because these much lower values have an impact on the mean that makes it not where you might think it would be, but pulled to the left of that. the skewed left, and that's really what that refers to. It's skewed to the left because the mean is pulled to the left. Another way to think of it, though, is that you're actually stretching this tail out to the left, as opposed to this one that's not stretched. A little more about this. I'm going to get rid of the other stuff except the table here, or the histogram we can look at. The mean for this data set is 6.3. You could calculate that if you want. I'd erase the data set, but it's just you add them up and divide by 10. The median is 6.5, and this is actually the point of what we're looking at, or how we're looking at this. The mean is pulled to the left. And this is always the case for skewed left data. The mean is less than the median. That's what skewed left means. We saw something similar with symmetric data set, that first one we did. The mean and the median were equal. That's what symmetric is. Skewed left is when the mean is pulled to the left of the median. And then finally, with this data set, you can tell from the list of numbers, you can actually tell right away from the histogram which is the most frequent data value. It's 7. The mode is 7. So all three of these are different. I think they were all the same for the symmetric distribution that we looked at. The mean, median, and mode were all the same. Now for a symmetric distribution, the mean and the median have to be the same. When I mentioned that bimodal distribution, that's a situation where you can have a symmetric distribution, but the mean and median are not equal to the modes. There's more than one mode, and they're different from the mean and median. So this is the skewed left situation. I have another example that'll introduce the other way, the skewed right. So let's look at those. Now let's look at those data values. That's one example. For this example, my data is 6 4 7s, 3 8s, a 9, and a 10. And again, this is a data set of size 10. And we're going to build the histogram. So histogram looks like, well, I need my number line for my data values or my X values. 6, 7, 8, 9, and 10. So 6, 7, 8, 9, 10. My data values, my frequency axis. I mean, you can put it over here at 0 if you want, but there's nothing going on here. So you might as well just put it here a little bit to the left of 6 so you can see the blocks well when we build the histogram. But the frequencies, the largest one is 4. So my frequencies, my first block is just the single 6. There's only one of those. Like I said, there's 4 7s, so the 7 block is going to go all the way up here. The 8, there are 3 8s, 1 9, and 1 10 to make the histogram. Now again, this one looks like it's kind of tipped to where it's leaning to the left. This is called skewed right. Say that mean is pulled to the right. It's not the hill that's pushed to the left. What's happening here is the data is stretched out to the right, and the mean is pulled to the right. And in this case, the mean is 7.7, and the median is 7.5. So this is kind of similar to what we've been seeing with the mean and the median before, except this time, the larger one is the mu. The mean is larger because it's pulled to the right. The median is not as sensitive to those large data values that are pulling the mean to the right. The median is more stable. Resistant is another name for that. By the way, the mode is again 7. There's more 7s than anything else. So the mode is a really kind of a simple thing. The median's not really difficult. I mean, it's just the one in the middle, or the average of the two in the middle if it's an even data set. Yeah, that's where that 7.5 came from for the median. The mean is probably familiar to you, just the regular average. So they're not really exotic concepts, but this relationship of looking at the relationship between the mean and the median, that's really what skewness is about. Now, it's easier to see, I think, from a histogram, but that's what it really means. If the mean is greater than the median, that's a skewed right distribution. And I'm going to make a sentence that kind of says that too, because that's the real concept of skewness. The mean is more distorted by skewness in the data than the median. Is. There's other ways to say this. Skewness distorts the mean more than the median. Or the mean is more distorted by skewness in the data than the median is. I want to do a quick summary of those. We saw really three things. The mean being equal to the median. That means the data set is symmetric. And it's in the histogram, it's the same sort of symmetry that you're familiar with. It's the kind of the same shape or mirror image on the two sides. Skewed data isn't like that. So we had to first, we skew left first. Skewed left is when the mean is pulled to the left. The mean is skewed to the left by low data values, and then mu greater than, if the mean is greater than the median, that's skewed right. There's a summary of the real meanings of these three terms. Now you have to do some exercises and practice stuff to get familiar with what it means for the data and the numbers, but mainly the histogram. If you can understand these three in terms of the shape of the histogram, you're halfway there. The other half is understanding what it means about the median and the mean, if they're the same, or if one is bigger than the other.